So let us apply this theorem which we proved on the Schwartz space. So first we will start. So compute the Fourier transform of f of x equals e power minus x square. So this is what we left last time as a incomplete, namely I brought it to the contour integral and asked you to do it and promised you that I will do it in a different way. So now we will do it. So clearly we have already seen f belongs to S of R. This is a standard prototype example we have. Now df by dx at x plus 2x f of x is 0, because if you just differentiate it, you get df by dx is minus 2x e power minus x square. So df by dx plus 2x fx equal to 0. So f is in S of R, xfs is also in S of R. So you can now apply the Fourier transform. Apply Fourier transform. So what do you get? I am differentiating, which means I must get 2 pi I xi f hat of x xi. That is what I get from df by dx. Then plus 2 times x f of x if I take the Fourier transform, that is minus 2 pi I times the Fourier transform, I mean derivative of the Fourier transform. So you have 2 by minus 2 pi I times df hat by dx at xi equal to 0. So simplify, you get df hat by d xi at xi plus 2 pi square xi f hat xi equal to 0. So from this we can easily evaluate. We know how to solve this linear differential equation. Multiply by integrating factor. So f hat of xi will be some c times e power minus pi square xi square. That is the solution of this differential equation. So now we take c equal to f of 0, okay, but f of 0 is what? C is equal to f hat 0. F hat 0 is equal to integral over R of e power minus 2 pi I x, which is 0. So the e part will not come. So e power minus 2 pi I x xi, and this is 0, and therefore this whole thing will disappear, just f of x dx, which is equal to integral over R e power minus x square dx, which we know is root pi, and therefore we have f hat xi equals root pi e power minus pi square xi square. Okay, so this is a very simple application of the previous theorem which we proved to compute the thing. We will do one more example, and this is the heat equation. So we consider the following initial value problem: du by dt minus Laplacian of u equal to 0 for xt in Rn cross 0 infinity, t is in 0 infinity, and u of x0 equals some u naught of x. So this tells you if you have an infinite bar which is kept initially at temperature at u naught of x, and then the heat is allowed to diffuse according to the law of diffusion, then the temperature at any time t in the bar, in the infinite bar, will give you the is given by the solution to this problem. Okay, so let us assume u naught is in S of Rn, the initial data is very good, okay, and that x going to uxt belongs to S of Rn for all t positive. So then you can, then we get treating t as a parameter, taking the Fourier transform, du by dt will be just du hat by dt at psi t. So t is just a dummy here, so you just get that, plus, so you have Laplacian. So if you use the law for the differentiate Fourier transform of a derivative, each time you pick up a 2 pi I, so you get 4 pi square times mod xi square u hat xi t equal to 0. This is for xi t in Rn cross 0 infinity, and you have u hat xi 0 equals u hat 0 of psi. I have just taken the Fourier transform. This is true for all psi in Rn. So this is for all x. Okay. So now you just solve this, treat t as a parameter and just solve this equation. I mean treat xi as a parameter. So you, and take here, and taking Fourier transform with respect to x. Now you treat xi as a parameter. Then what do you get? You have a ordinary differential equation with a certain initial value as far as u hat is concerned. So u hat of xi t equals u naught of xi, u naught hat of xi into e power minus 4 pi square mod xi square t. Okay. So now we want to recall two facts. One is, if you have the product of two Fourier transform, that is the Fourier transform of the convolution. So we will, and secondly, we know that the exponential for e power minus x square has e power minus x square pi square mod xi square as the thing. So now we are trying to write this as the Fourier transform of a suitable function. So let us do that. So e power minus 4 pi square mod xi square t is equal to e power minus pi square into 2 root t mod xi square. 4t pi square is minus pi. So it's e power pi square, and instead of xi square you have 2 root t. So it's like taking scaling the e power some lambda. So we have already know that if you have f of x by lambda equals g of x, then g hat of x xi is lambda n f of f hat of lambda x. Okay, so lambda here is 1 by 2 root t. Okay, that is, we are taking lambda as 1 by 2 root t. So this will be equal to, I am going to write pi to the minus n by 2 root t power n into pi power n by 2 by 2 root t power n, and then e power minus pi square 2 root t mod xi whole square. So that is the lambda xi. So this is of that form, pi power n by 2 by lambda power n is also there. Okay, so lambda power n you have this, and therefore so this is lambda power n, and this is f hat of lambda xi. Okay, so this is nothing but you have 4 pi t to the minus n by 2, okay, into g hat xi, where g of x is equal to e power minus mod x square by 4t, that is 2 root t whole square. Okay, so this thing. So hence, so you have this as the convolution, product of two convolutions. So from this I mean product of two Fourier transforms, and that is the Fourier transform of the convolution, and therefore you have u of x t must be the convolution of these two functions. So there is a 4 pi t to the minus n by 2, which is outside in this expression, and into u0 star g at x. Now u0 and g are all in S of Rn, and therefore you have that the convolution is, both of them are in L1, so the convolution is well defined, and therefore you can explicitly write u of x t is equal to 1 by 4 pi t to the n by 2. This is a very familiar formula you might have already seen when studying PDE somewhere else. So e power minus mod x minus y whole square by 4t into u0y dy, and this is true for t greater than 0. So this is the formula for the solution of the heat equation, assuming of course that you have u0 is in S and ut is also in S. So and you do have a solution. Therefore if you have u naught in S, you know u can be written in S, and this is the solution to this. Now if you consider ext is equal to 4 pi t to the minus n by 2 into e power minus mod x square by 4t into h of t. This is a fundamental solution for ut minus delta u. Okay, the heat operator. Okay, that can be, so a proof can be found in the book of Treves. Okay, partial differential equations. Okay, so now this is somewhat, so if you take the convolution of this, so here we are taking only for t bigger than 0, and therefore you had h of t is 1, h is the Heaviside function. So remark, suppose u naught has compact support. And say u naught is greater or equal to 0. Then, so call this star. Star implies for every t positive, ut is, so u of xt is strictly positive for all x in Rn. Okay, so this is called, so you have this, suppose you were in real line and you have u naught is positive and it has support here. Instantaneously the heat is felt throughout the rod. This seems counterintuitive, but it is true. Of course one can show that it's in fact, it will be very small at as you go far away, but still it will be non-negative, and so instantaneously the heat diffuses throughout the thing. So this is called the infinite speed of propagation of signals. This is the technical term in PDE. Unlike the wave equation, which will have a finite speed, that means if you have initial data of compact support, the solution at any time t will also have compact support. So if you switch on a light, it won't become bright everywhere, it will only be bright inside the light cone. We will see that later on. So, but in the case of the heat operator, the moment you have heating, instantaneously for every positive time you can feel the heat everywhere. Of course not very hot, but still you can feel it. Okay, so now we will continue with the Fourier transform and how one can generalize it to other classes of functions.